Oh! Oh! Oh man! Oh my God!
Alright, so our problem today is that we're trying to find the force of impact of a squash filled with aluminum compared to a regular squash.
For our equation, we had a couple variables. D represented impact distance, H, the height of the house, T, duration of the fall, BC, critical velocity, A, deceleration, and M, mass of the squash.
Alright, so we got a couple known variables. Our initial velocity was 0 meters per second because we just dropped it off the top of the house. Our derivative of the position formula is going to equal our critical velocity. Our deceleration is going to equal our final velocity minus the critical velocity over 2 times the impact distance over here. And our final velocity is going to equal 0 meters per second because the squash smashed into the ground and it's not moving anymore. Our force of impact is going to be mass of the squash times the deceleration of the squash. So let's get started. Squash 1 had a mass of 1.36 kilograms. The house was 6.3 meters tall. The impact distance was 0.025 meters, and the time it took to hit the ground was 1 second. Plug that, we get our position formula ready right here. We find the derivative of that, plug in our time, get a critical velocity of 19.62 meters per second. Then we plug that into our deceleration formula, the 0 meters per second being the initial velocity, or the final velocity right here, minus the critical velocity squared, over 2 times the impact distance, 0.025 meters. Then we get this equation, negative 384.94 meters squared per second squared over 0.05 meters. That gives us a total deceleration of negative 7,698.8 meters per second squared. If we plug that into our force equation, we get 10.47 kilonewtons of impact force.
Awesome. So now we have the second squash. The second squash was the one that we filled with aluminum. So it had a mass of 2.04 kilograms, and the height and the time were the same, but the impact distance, which is the distance it concaved in, was 0.013 meters. So we, like the first squash, we have the position formula. We did the derivative to get the critical velocity, which is negative 19.62 meters per squared, meters per second. And so then we plug that into the deceleration, which the top is the same, but however the bottom is different because of the impact distance is different. So we plug those numbers in, and we get the final deceleration of negative 14,805.38 meters per second squared. We plug that into the force equation, and we get a mass of 30.2 kilonewtons.
Yep.
The wave and frost effect half failed us. Okay.
Oh, that's... Oh! Oh, man. Oh, my... It took 0.15 seconds longer.
Stop.
Oh, that's... Oh! Oh, man. Oh, my... Oh, man. Oh, my...